let's look at another object rolling down a ramp, a hollow cylinder, and see if we can show the acceleration is 1/2 g sine theta, which would be a little bit less than the hollow sphere that we just looked at in example number 1. And so we know if we're looking at acceleration, we want a free body diagram, and so some more practice here. And so I like to mark the center and the contact point. And that helps me make sure my forces originate from the point they're applied. And so weight, or mg, comes from the center, normal force right through the center and on up perpendicular to the ramp, and then friction, static friction, parallel to the ramp and up the ramp opposing the motion. Let's, instead of solving the torques about the contact point, which may seem a little strange to people, but that is a legitimate way to think about rolling, let's sum the torques about the center and see how that goes. And so the sum of the torques equal I alpha about the center. And so what forces have a torque now? The normal force is applied here, and this is the rotation axis, so there is a lever arm, the radius, but the normal force is parallel to the lever arm, so it has no torque. How about the weight? The weight is applied at the center is the rotation axis, so the weight has no lever arm. And what about static friction? It's applied at the contact points. The rotation axis is the center, so it does have a lever arm R, and it is perpendicular to that lever arm, so friction, static friction, has a torque about the center. And so static friction times the lever arm equals I alpha. How about I? Well, for a hollow cylinder, you need to know what that one is. They won't give you that equation. It is the same as for a point object, mr squared. And so we can put that into here. And since we're solving for the linear acceleration, we want to substitute for alpha. And so a is alpha r, so alpha is a over r. And so we're going to put that into there. And we get some simplification. I can cancel out that r. I can divide both sides by r. And I'm left with static friction equals ma. So I haven't shown what I need to show, but I've made some progress. The missing piece here is this object is also translating down the ramp. It's accelerating, and so we can sum the forces and get another equation. And so I draw my coordinate system with positive x in the direction of the acceleration, and we can apply Newton's second law, sum of the forces in the x equal ma. And so if we look in the x direction, we have part of the weight. Again, here's angle theta, and so this would be theta here. And the perpendicular component that applied torque in our first example is now the x component of weight down the ramp, good old mg sine theta, and then minus the force of friction. So sum of the forces in the x is mg sine theta minus the force of static friction, and that equals ma. And so we can take our result here and eliminate the unknown static friction force. It is not equal to mu n in this case, or at least we don't know that. It would equal mu n just before it started to slip. And so you can't assume that you know what the static friction force is. Remember, it's less than or equal to mu static times the normal force. And so now we have some simplification. The m goes, divide every term by m, and we can add a to both sides. And so that gives me g sine theta equals 2a, and a is 1/2 g sine theta. And so again, this is a very difficult skill. It takes practice if you want to learn it. Watching me do it won't really help that much. Using what I did to learn it yourself is the way to go. And so why don't you try summing the torques about the contact point on this one and seeing if you can get the same result, or go back to example number 1 and see if you can use this and apply it to a hollow sphere. Good luck.